Aberdeen in the far north of Scotland, shown by the red dot there. Our latitude is 57 degrees north, so it's just a little bit south of St. Petersburg, I think. Quite similar latitude. That's the main university campus. It was founded in 1495. Aberdeen is also the place where the world's first whole-body clinical MRI scan was done in 1980. And that's a picture of the scanner there with Jim Hutchison lying inside it, pretending to be a patient. And that's the first clinical scan from 1980 there. Excuse me. So a summary of my presentation. First part will actually be a tutorial on the basic physics and concepts of MRI. Professor Chiswick asked if I would include a teaching element in my talk, so I'll be doing that for the first 15 minutes or so. And then I'll move on to the second part of the talk, which will be our research in fast field cycling MRI. Okay, so first of all, part one, basic physics of MRI. My apologies to MRI experts in the audience. This will be extremely basic for you. So what's the central idea behind MRI? Well, the central idea behind MRI is shown in this picture here. So you might wonder why a football field is the central idea behind MRI, because it's a rather special football field. I didn't take this picture, I just grabbed it from the internet years and years ago. It's a slightly unusual football field because it's on a little bit of a slope. It would be difficult to play a match there, I think. But nevertheless, this is the central idea behind MRI because it's a field gradient. It's a field on a gradient. And of course, in MRI, we use a magnetic field gradient. Not quite the same thing, but anyway, a little joke there. So a magnetic field gradient is a linear variation of the strength of the applied magnetic field with position across the bore of the scanner. That's its definition. So without a gradient, the magnetic field in the Z direction is B naught everywhere, 1.5 Tesla for example, if it's a 1.5 T system. With a gradient applied in the X direction, just as an example, that would be across the bore of the scanner, then the field becomes Bz of X equals B naught plus X times Gx, where X is the position in meters and G subscript X is the strength of gradient in Tesla per meter. We can show this by field arrows. So this is the horizontally, we have the X the position across the bore of the scanner. These black arrows indicate the strength of the applied magnetic field from the scanner's main magnet, and that would be, say, 1.5 Tesla everywhere. It's the same everywhere. Then when we switch on the current in an X gradient coil, we have this additional field generated, which is along minus Z on the left-hand side, along plus Z on the right-hand side, and varies linearly from left to right. So that's the gradient field given by Bz of X equals X times Gx. And of course, the field experienced by spins within the scanner is the sum of those, the black arrows and the green arrows, these blue arrows. So we have a linear variation of field strength going from the low field on the left through the standard field, 1.5 Tesla, for example, in the middle, to a higher field on the right. And you can see it's a linear variation, and the total field then is given by B naught plus X times Gx. So that's when we apply a gradient in the X direction. Now, magnetic field gradients are used in three distinct ways in MRI. And we'll look at a couple of those in detail. So in frequency encoding, magnetic field gradient is used to give spatial location along one direction, for example, the X direction. In selective excitation, the field gradient is used to determine the position and thickness of the image slice in the slice tomographic image. For example, a 1 centimeter thick slice in the transaxial plane. And it's used in phase encoding to give spatial location along the orthogonal direction. So that, for example, the Y direction, the vertical direction in the scanner. So these are the three main ways in which magnetic field gradients are used. And virtually every MRI pulse sequence uses gradients in these kinds of ways. Okay, so let's look first of all at frequency encoding. So we're going to try and get spatial information along the x direction, the horizontal direction across the bore of the scanner. And as an example, we're applying a magnetic field gradient along the x direction, Gx equals 0.5 millitesla per meter, a moderately weak gradient, but that's the kind of strength of gradient that one would typically use. So here's our happy patient lying on his back in the center of the scanner. Any spin, and we're going to be collecting NMR signals with the gradient present. So we are going to apply the gradient, and we're going to measure NMR signals with the gradient present. So any spins on the center line at x equals 0, it's the patient's nose and anything on the central line. The local field there will be unaffected by the gradient. So the local field will be 1.5 Tesla, and the local Larmor frequency for protons will be 63.9 megahertz. And that's illustrated by this sine wave there, which is meant to represent that center frequency. Spins on the patient's right arm are actually over to the left of the center of the field of view. So, for example, about 25 centimeters to the left of the field of view, of the center of the field of view. So with a positive gradient being applied, that's in the low field region. So the local field at that position of the patient's right arm is actually lower than 1.5 Tesla. It's 1.499875 Tesla with this gradient strength and this distance offset. So the local Larmor frequency is 63.895 megahertz. So that's actually 5 kilohertz less than the central Larmor frequency. And there that's illustrated as a lower frequency sine wave. And then any spins on the patient's left arm, they're to the right of the center of the field of view, to the right of the isocenter. And so their local field is high compared to 1.5 Tesla, and the local Larmor frequency is 5 kilohertz higher than 63.9 megahertz. And that's illustrated there as a higher frequency sine wave. So of course, everything, all the whole body is inside the scanner, is inside a large RF coil which transmits the excitation pulses and receives the signals. So all of these signals will be received at the same time. So let's look at this in a slightly different way. So suppose we have our scanner and we put 3 bottles of water at different positions across the bore of the scanner. So suppose we put a large bottle of water, a large tall bottle of water on the left-hand side. That will give a large amplitude, low frequency signal. Suppose in the middle we have a small bottle of water, still a thin bottle of water, but a small bottle containing much fewer proton spins. So that will give a small amplitude, medium frequency signal. And if we have a medium-sized bottle on the right-hand side, that will give a medium amplitude, high frequency signal. So all of these 3 signals would be obtained simultaneously. And the total signal would look something like that. If there are 3 distinct frequencies, then the total signal will be a sum of those 3 sine waves to give the time varying signal that would look exactly like this, with the 3 frequency components contained in it. And that's just a repeat. Then what we have to do is to do a frequency analysis of the time varying signal to recover the components, and we do that by digitizing the signal and putting it into a Fourier transform algorithm. And the output of the Fourier transform algorithm can be displayed as a histogram of the magnitude, and we see 3 peaks: a peak for the low frequency signal, a peak for the medium frequency signal, and a peak for the high frequency signal, and the amplitudes of those peaks just correspond to the amplitudes of the original signals. So here, without any further data processing, what we have is a one-dimensional projection of the object or objects inside the scanner along the gradient direction. So that's essentially a one-dimensional imaging experiment called frequency encoding. How do we actually do the experiment? So you might think this would be the way to do it. This would be the pulse sequence. So this is as a function of time. We have a 90-degree excitation pulse there. We're switching on the X gradient just after the 90-degree pulse there. And in the presence of that stable X gradient, we're measuring an FID signal like this. So in principle, we could do it like that. But in practice, we can't, because we cannot switch on the gradient waveform instantly. We have to switch it on in a kind of ramped, slow ramped fashion. It can be pretty fast. It can be less than 1 millisecond, certainly. But we cannot turn it on instantly because of the fact that it's generated by sending electrical current of hundreds of amps through a coil of wire, which has inductance and resistance. So it will have a certain time constant. So unless we have infinite voltage, which we wouldn't like to have anyway, we cannot turn on the gradient instantly. We can only turn it on in a ramped fashion. And if we did that and tried to measure NMR signals during the switch on ramp, that would corrupt the spatial information. So we don't want to do it that way. What we want to do is to delay the NMR signal until such time as the gradient has stabilized, around about here, for example, and then there won't be any problem with corruption due to the turn on ramp. And the way we do that is by generating a gradient echo signal. So this is formed by manipulating the magnetic field gradient, not by 180-degree refocusing pulse. So this is the pulse sequence we would actually use to generate the gradient echo. So there's a 90-degree excitation pulse. First of all, we apply a negative gradient along the X direction. Then we reverse the polarity of the gradient to apply a positive gradient. And it's under that positive gradient that we measure the signal, which is in the form of an echo signal called the gradient echo signal, like so. So there's the first part is a negative gradient. That just means we go from high field on the left to low field on the right. Then we switch it to a positive gradient, which is just low field on the left, high field on the right. That's all we mean by a positive gradient as opposed to a negative gradient. This is going to show what happens in a positive gradient. So before we apply a gradient, all the spins are at the same field, so they all precess at the same frequency as a function of position. If we now introduce positive gradient, then the spins on the left are going slower, and the spins on the right are going at the fundamental Larmor frequency, and the spins on the right are going faster because of the fact that because of the magnetic field gradient giving a change in field as a function of position across the X direction. So that's essentially what a gradient does in terms of winding up the spins. And here we show the formation of a gradient echo. So here we have the waveform at the top, and you can see the progress in time with this vertical line going across. And you can see during the first part, the spins wind themselves up, like so. And then with the positive gradient being applied, the initial winding up is rephased. Spins are rephased, and they form, when they come back into phase, they form the gradient echo. So that's dephasing, followed by rephasing, and gradient echo would be now, and then dephasing again. So that's how the gradient echo is formed, like so. And the center of the gradient echo will occur from when the amount of dephasing is equal to the amount of rephasing. So when this area B is equal to the area A, that's when the center of the gradient echo will occur right there. So it's easy to predict when the gradient echo will occur. The next method I'm going to speak briefly about is selective excitation. So this is how we excite spins only in a thin slice. So suppose this notebook is sliced, the 1 centimeter thick slice that we want to image in the patient's brain, like that, for example. Then we use selective excitation to do that. So we limit the excited spins to be only those spins within the slice plane. So, for example, if we want to image a transaxial slice in this patient's body, so that's in the XY plane, the transaxial plane. So the first thing we do is to apply a magnetic field gradient. Before we do anything else, we apply a magnetic field gradient in the Z direction. That's the direction perpendicular to the slice plane. And with a gradient of 2.35 millitesla per meter applied, that's equivalent to 100 kilohertz variation of Larmor frequency per meter. So that means that at that position down there, half a meter along the plus Z direction, the local Larmor frequency is 63.95 megahertz. That's 50 kilohertz above the fundamental alarm frequency. Whereas if we go half a meter in the other direction to the patient's head, the local alarm frequency there with the gradient applied will be 50 kilohertz below the fundamental alarm frequency because of the gradient. Then what we do is to apply a shaped RF pulse, and typically a sync-shaped RF pulse is used applied at the fundamental alarm frequency, 63.9 megahertz for 1 Tesla field, and that contains frequencies within a narrow bandwidth. So, and that depends on the timing of the pulse. But for example, we might have a 1 kilohertz bandwidth of the RF pulse. So that means it contains frequencies from 63.9 megahertz minus 500 hertz to 63.9 megahertz plus 500 hertz for 1 kilohertz bandwidth. So the only spins to respond to that RF pulse will be those whose resonant frequency is contained within the pulse. So these spins here, their resonant frequency is way too high. It's much higher than anything within the RF pulse, so these spins just do not respond. Likewise, spins in the patient's head, their alarm frequency is much lower than any frequency contained within the RF pulse, so these spins do not respond either. Even though they're within the RF coil through which the RF pulse is transmitted, these spins do not respond. And the only spins that do respond are the spins within the 1 centimeter thick slice. Those are the spins that we want to excite. So that's how selective excitation works. And the final method I'll speak very briefly about is phase encoding, and the phase encoding is used to obtain spatial information along the orthogonal direction, that would be the y direction here. So spatial information is encoded into the phase of the NMR signal. Whereas in frequency encoding, it was the frequency of the signal. Now we're going to use the phase of the NMR signal. So the NMR signals are measured following different amplitudes of phase encoding gradient. And for a 256 by 256 matrix image, the pulse sequence is repeated 256 times to do that. So there's the pulse sequence, which is repeated n times, so 256 times for a 256 by 256 image. There's the first 90-degree pulse with the selection gradient. There's the frequency encoding gradient there, and that's the phase encoding gradient. So each time we repeat the pulse sequence, so there's the first repetition there. We repeat it with everything the same except for the phase encoding gradient, which is stepped in amplitudes. So it goes from the largest positive there to the next size down there. So that would be plus 128 units. For a 256 by 256 image, that would be plus 127 units, and so on in a stepwise fashion. And that's the repetition time, and that's the echo time. So just briefly, I'll show you how the data is collected. So there's the first time the pulse sequence is applied with the largest positive phase encoding gradient. That generates this gradient echo signal here. We digitize that signal, take 256 samples of it, and store the data in the raw data matrix, first line raw data matrix. Then after some delay time, TR, we apply the pulse sequence again and collect a second gradient echo signal, which we store, and then the third time and the fourth time, each time updating the size of the phase encoding gradient amplitude. So at the end of data acquisition, we have 256 samples collected. That's the raw data matrix. Then we do a two-dimensional Fourier transform to generate the image. So we do that first of all, we Fourier transform each row like so, and then that generates an intermediate data set shown here. And then we Fourier transform each column. And once we've done that, that is the image, which can be displayed as a magnitude image like so. So that's how we collect the data. This is what the MRI raw data would look like as a stack plot. So largest signals in the center of the raw data map, which is also referred to as K-space. And the pulse sequence covers K-space line by line. So that would be the first line, the first gradient echo signal is the first line of K-space, and the second line, and so on and so on. And then the route through K-space, followed by the pulse sequence, is called the K-space trajectory. Okay, so that was a very rapid tour through the very basics of MRI for those in the audience who haven't seen that before, in case there are any. Okay, so now I'll move on to the research part of the talk, when I'm going to be speaking about our group's work over the last decade or more on fast field cycling MRI. Incidentally, these pictures I'm showing are pictures I took in various parts of Scotland. That's way over on the west coast of Scotland, where it's very beautiful. Okay, so it's well known and has been known since the very beginning of MRI that much of the contrast arises from differences in the T1 relaxation times of tissues. Of course, T2 can provide contrast as well, but T2 is very frequently used to generate image contrast. So this is a typical T1 weighted proton MR image. You saw some beautiful images in the previous slide, so you know well what MR images can look like. This is actually quite an old image, and even better ones can be obtained now for sure. Anyway, you can see the structures in the brain very nicely there because of the different T1 weighting of the different tissues. Grey and white matter, for example, different T1s, so give different image intensities in the T1 weighted image. But what's less well known is that T1 dispersion can give disease-related information. Now, T1 dispersion is just the way in which T1 changes with magnetic field strength. So a T1 dispersion plot is a plot of T1, the vertical axis, versus magnetic field strength or lumbar frequency on the horizontal axis. And over the years, many measurements of T1 dispersion in normal and diseased tissues, both animal tissues and human tissues, have been done in many labs, including our lab. And these studies have shown indeed that T1 dispersion, the shape and position of a T1 dispersion curve, could be a marker of disease. So could be used for diagnosis, potentially. But this T1 dispersion information is completely hidden to conventional MR scanners because each scanner can only operate at its own fixed value fields. So for example, 1.5 Tesla scanner produces great images, but only at 1.5 Tesla. 3 Tesla scanner likewise, and 7 Tesla scanner likewise. They all produce great images, but only at their own native field strength. So none of these scanners can be used to measure T1 dispersion, because to measure T1 dispersion, you have to be able to change the magnetic field to different values during measurement signals. So you cannot use T1 dispersion as a biomarker in standard MRI. Nevertheless, that's what we set out to do 10 years ago or more. We want to use T1 dispersion as a new kind of contrast ultimately in clinical MRI. So here is a cartoon of a dispersion MRI machine. More of that later. And so what we want to do is to put the patient inside the scanner and to measure, probably in a spatially resolved kind of way, dispersion curve. So this shows relaxation rate, 1 over T1, as a function of field strength or lumbar frequency equivalent. So for normal tissue, we might see a dispersion curve like as shown in blue there, whereas in diseased equivalent tissue, you might see a different level of dispersion curve, indicating overall different T1s, and perhaps a different shape of dispersion curve as well, with some wiggles in it, like is shown here. And so what we want to do then is to use the shape and position of the dispersion curve as a marker of disease, as a biomarker of disease, and to do indeed that in human samples in patients. Okay, so a little bit more about the motivation first. So before I come on to the imaging aspect, so in our lab we have a benchtop reflexometer. It's a commercial reflexometer made by the Stellar company in Italy. So it contains control electronics and amplifiers and so on, and the magnet in this right-hand box. So it's a small magnet, and you can place a test tube like the one shown here into the hole in the top, and then that goes into the magnet. And you can use that to measure T1 dispersion curves in quite a short period of time. So it takes about 1 milliliter samples. So we put in an ethics application, which was accepted, and with patients' permission, with patients who were having a mastectomy, breast removed because of breast cancer, We took samples of their mastectomy tissue after surgery, and we placed those samples, about 0.5 milliliter volume samples of tissue, into this device. And we were able to measure relaxation rate 1/T1 as a function of alarmar frequency. It's the log-log plot, down to very low magnetic field strength there. So from about 10 kilohertz up to about 10 megahertz alarmar frequency. And that's the curve, that's the dispersion curve that you see in the tumor tissue. That's from the center of a patient's tumor. Whereas if you make a measurement, because when the mastectomy is done, normal tissue is removed as well as the diseased tissue, of course. Surrounding normal tissue is removed as well. If you make a dispersion measurement of normal tissue, it looks very different. It's a much flatter curve, and it doesn't have these bumps in it there. So just by looking at those curves, if you could make those measurements in vivo in a patient, you could certainly tell which was normal tissue and which was diseased tissue. So that's part of the motivation for this. And perhaps even more interestingly, if you take a sample of breast tissue from the periphery of the tumor, actually tissue that looks visually normal, and make a dispersion measurement of it, then clearly it's not normal, because the dispersion curve from that tissue in the penumbra of the tumor looks much more like the dispersion curve of the tumor rather than the dispersion curve of normal tissue. So that's clearly tissue which is on its way to becoming cancerous. So that would be very useful information to have for the breast surgeons to guide them into which tissue to move and which it's safe to leave behind. Okay, so that's just the motivation. Some of our clinical results, as well as the motivation for doing this in imaging whole body fashion. So how does field cycling work? Well, this device that I showed before uses field cycling. It's a field cycling magnet which is switched up and down in order to measure T1s at different field strengths. So essentially, we want to use that technology in a whole body scanner, which is what I'll show you soon. So how does field cycling work? So in field cycling MRI, magnetic field is switched between 2 or more levels during the pulse sequence. So you can see the dot there moving along as time progresses. So it goes from high field to low field, and it's at the high field part. So it's at the high field part that we measure the NMR signals, as it's shown there, and we can switch to different values of low field in order to explore the magnetic field dimension of the dispersion plots. So this is a generalized FC method, such as is used in the stellar reluxometer as well. So we start off by polarizing the spins at high field. That would be at the highest field that the instrument can manage. Then we rapidly switch to what's called evolution field, B0E, and that's the field at which we want to measure T1. So at that field, usually a lower field, the spins re-equilibrate with a time constant given by the T1 of the sample at that field strength. So relaxation occurs there. And then we switch again rapidly back up to the original field for the detection period. And it's at that field that we apply the 90-degree excitation pulse, measure the NMR signals, and also apply the imaging field gradients in an imaging experiment. By the way, the field ramps are indeed short. They have to be short compared to T1, and in order not to lose information about T1. And if the field ramps are short, then the method is called fast field cycling. So let's look at some hardware that we've built. Indeed, this is our latest prototype FFC scanner. So we have two whole body prototypes. This is the latest one that we've been building up over the last 10 years or so. So it has a resistive magnet underneath this green potting material here. Is a resistive magnet with 3 parallel coils. And if we send 650 amps through each of them, that generates a field up to 0. That generates a field of 0.2 Tesla, which is the highest field of this particular scanner. The scanner also has these coils here. The gray coils are or environmental field correction coil. So this allows us to cancel the Earth's magnetic field, the local Earth's magnetic field, which is about 50 microtesla, by sending the correct current through these coils. There are 3 Helmholtz pairs along the 3 principal axes. So if we measure the field distribution, then we can know what field to send through the coils to cancel out the Earth's magnetic field. This allows us to go to field strengths even below the Earth's field. We've done measurements down to 10 microtesla or even less. And we have a head RF coil there. And of course, for imaging, the head has to be in the center of the scanner. And the couch allows us to move the patient into the center of the scanner. It's quite a claustrophobic device, I have to say. The bore size from there to there is only 50 centimeters. So it's not for people who are claustrophobic for sure, but it's not for people that are very big either. But this is Lionel Broche, my colleagues, and he fits in quite well, and I fit in quite well as well. This has been published in Scientific Reports in 2019, details of this instrument. And it is indeed suitable for patient studies. So it has a communication system, it has a panic button, it has airflow, lighting, and even the music system is included. These are the big power supplies that send the 650 amps times 3 through the magnet coils. These are radiofrequency coils. We build all our own coils. These are 3 generations of head coil, including a 3D printed version. It's a knee coil, and these are breast coils. We've been looking recently at array coils. So that would be a 6-channel array for torso imaging, 3 coils on the top of the body and 3 underneath. These are images of volunteers. That's a brain image at 200 millitesla. That's the 0.2 Tesla. That's the highest field of the scanner. Those are knee images, and these are breast images at 200 millitesla and at 1 millitesla. So this is the field cycle image going down to 1 millitesla, and despite that incredibly low field strength, 0.001 Tesla, the field strength, the image quality rather, is actually quite good, and that's because of the field cycling. So I'll show you some clinical related results in the last few minutes. First of all, in osteoarthritis, so patients undergoing joint replacement surgery had agreed to have FFC measurements made on the joint tissues after they've been removed. This is not an imaging study. This is going back to the relaxometer that we saw before. So that's what the excised joint looks like, and that's a core from that joint was placed in the sample tube and then into the relaxometer. And there you can see we see very different dispersion curve between healthy cartilage and osteoarthritic cartilage, especially the level of the curve is different, but also actually the shapes are different too. Incidentally, these peaks here that we saw in the breast tissue, breast tumor tissue as well, these are quadrupolar peaks, which are indicators of immobile protein. Our first clinical FFC study was in acute ischemic stroke and had the acronym PUFFINS, even has its own little logo. That's led by stroke consultant Dr. Mary Jo McLeod. And this is the first clinical study using FFC. So all patients have CT and most also have 3T MRI for comparison. And we image quite soon after the stroke. So that's in one patient. This is a CT scan. Not really much to see there unless you're an expert reader of CTs. But in the FFC scan, you don't see very much at 200 millitesla. Kind of a hint there, perhaps. But when you switch the field down to its lowest value, or one of its lowest values, 2 millitesla, then the stroke affected region really jumps out. The image quality here is not so good because this is a very early scan. And since then, we've improved the technology of the scanner significantly. So that's a relatively poor quality image, but nevertheless, you can see the stroke affected region jumping out at the lowest field when you switch the scanner to its lowest field. This is, again, conventional imaging from another patient with CT and 3 Tesla MRI. And again, when we switch to the lowest field, this time it's even lower, 0.2 millitesla. That's only 4 times the Earth's field. You can see the stroke affected region jumping out really very clearly, whereas it's much less clear at 0.2 Tesla. So this shows the value of imaging at ultra low magnetic field strength. We've also done a study on normal breast tissue from normal volunteers, and I'll skip through this. Just is a rationale for producing images at 4 different field strengths based on the breast cancer results. So these are results. These are images. These are inversion recovery field cycling images at different inversion times and different field strengths. So the different rows are at different field strengths, and we can generate calculated T1 images from those data. And we've also done some work and these are the R1 images, the relaxation rate images that we can calculate, and we've also done some work to parameterize those data to show the quadrupole peak amplitude, the high frequency component and low frequency component. So in conclusion, FFC MRI is a new imaging modality that does provide new information that's invisible to other modalities. It generates new kinds of image contrast, which is endogenous. It doesn't require contrast agents. It uses low fields, so it's safe and applicable in emergency situations. We've done patient studies using on stroke. Of course, these are currently subject to COVID restrictions, but we are hoping to restart them very soon. We've done breast volunteers. We've done breast cancer studies as well. We've done brain cancer. So far, only 2 patients, but we're hoping to restart those soon. And a full imaging osteoarthritis study is also being planned. We're currently building a new FFC scanner, which will be located in our teaching hospital as opposed to the medical school. So we'll have access for all patients. These are the people that have done the work in Aberdeen. And this is a list of some of our external collaborators. And these are our present and recent funders. That's our website. And thanks for your attention. By the way, that's a cycle in the field. So that's all. Thank you very much for listening.
Great. Thank you very much, David, for an impressive presentation. Let's see if we have questions. Yeah, see, Andrei Kamolkin is asking a question. Go ahead, please.
Yes, I have one question. On the photo with your scanner, I did not find any cooling equipment, but power consuming during polarization and registration, you saw is about 100 kilowatt.
Yes,
what
it
about,
is indeed. Yes,
about?
it is indeed water cooled. So you can't see any of the cooling, but the whole magnet is water cooled. There's water flowing through it at quite a large rate. So yes, we have to get rid of about 70 kilowatts, in fact, when it's running, because it's not always at full field. So there's a duty cycle there. But yes, 70 kilowatts we have to get rid of, and but we can do that.
Okay, thank you very much. Thank you.
I do have other questions. I actually have one, David. I'm wondering, when you field cycle over a patient head, I understand these are not very high fields, but still, does it cause any adverse effects like dizziness? I don't know, anything.
No, it doesn't cause dizziness, but there is one physiological effect, magnetophosphines. So if you're in the scanner, or even if you're close to the scanner, when it's switching, you see in your peripheral vision flashing lights that are not actually there. And this is because of direct magnetic stimulation of the retina. So it only occurs when you're in the scanner. It doesn't persist when you come out, and it's not in any way harmful. I mean, we're careful when we switch the field. We're careful to stay within the safety guidelines. So the safety guideline would say that you shouldn't ever switch the field in any MRI scanner faster than 20 Tesla per second. So we're switching typically about 10 to 12 Tesla per second when we switch the field up and down. So it's safe from that point of view.
Okay, thank you. There were other questions. I can see some hands disappeared. The Thomas Meersman is asking one thing.
Yeah,
Thomas?
just a quick question. Yeah, hello, can you hear me? Yes, so a quick question concerning the stroke image, the field cycling image. I mean, obviously that's very important to make a quick decision because there are two types of strokes there. How long does, I mean, obviously time is at the essence. How long does it take to record that image? I think it was a 200 millitesla and then field cycle it down to lower fields, but how long does it take to record that image?
Yeah, so if you're just obtaining an FFC image at 1 field strength, it doesn't take any longer than the standard MR image. I mean, if you don't use a rapid imaging sequence, it would take a couple of minutes, I guess. But we can also we can actually adapt rapid imaging pulse sequences like fast spin echo to speed up the data acquisition. So if you want to obtain full dispersion information, of course, there's the extra dimension of field strength to explore. But nevertheless,
you have an indirect dimension.
So yes, well, we can obtain single images quite rapidly.
And for to identify stroke, do you need this entire series of indirect? I mean, of field cycles, or can you go with an optimum cycle?
Yes, you don't particularly need the dispersion information as such. We found that the highest contrast is obtained in the lowest field strength, so around about one millitesla. So if you wanted to image a patient really rapidly, I guess you would just, in that case, just obtain an image at that field strength.
Great, thank you, David.
Beautiful.
Once again,
I
thank you
assume
very much.
that's
Thomas.